is Davi Lopes Medeiros, and I would like to talk about resonance sequences and how we must define them. First, we consider n positive real numbers. After that, you consider the positive multiplies of them. You consider the union of all multiplies. After that, we consider the elements of n in increasing order. And now, we define the multiplicity of nj, as the next slide shows. And thus, the resonance sequence of the initial set is defined as you can see. In the next slide, you can see some examples of initial sets and its resonance sequence. Okay? Now you can make the question, what you can say about the initial sequence given only its resonance sequence? And a surprise theorem due to Alvarez, Birbrair, Berendt, and Giroux says that if n is bigger than 2 and the elements of the initial sequence are positive integers relatively co-prime 2 on 2, then you can say that its resonance sequence completely determines the initial sequence. Now we must define what is combinatorial equivalence between two sequences. We say that two sequences are combinatorially equivalent if they generate the same resonance sequence. And the main theorem of the paper is about the complete classification of the initial sets with three elements under the combinatorial equivalence, as you can see in the slides. As you can see, we define some invariants, and the complete classification says that two sequences with three elements are combinatorially equivalent if and only if these invariants are respectively equal. Okay? So that's a necessary and sufficient condition for combinatorial equivalence with three elements. And resonance sequence appears in other branches of mathematics, like the geometric theory of ordinary differential equations has invariant of the linear equations of the second order under the focal equivalence. Okay? So that's it. Thank you for your attention.